the coefficient of determination, r squared. Previously, we've learned how to find the correlation coefficient, r, which gives us, of course, the strength of a linear relationship between two numerical variables. R squared gives us the coefficient of determination. Now, what this helps us find is how much of one variable's change can be explained by another variable's change. So as one's height increases, one's weight also generally increases. You can see there's a strong linear relationship, it's positive, and r, our correlation coefficient, is 0.8. So there's a strong linear relationship. But there's other factors than your height that also influence your weight. And so some of those other factors, obviously your diet, your genetics, all the rest of it, will come into play. Now, what r squared finds for us, so let's square r here, 0.8 squared, move my calculator so you can see it, 0.64, and if we gave that as a percentage, it would be 64%. This says that 64% of the change in someone's weight here can be explained by their height, and the remaining 36% of variation in weight is explained by other stuff. This is obviously just a guess. I have no idea what the relationship is. I've just made a cute little graph. So if we know someone's height, according to this, which is fake, we could predict their weight, and we might get about 64% correct. It's a little bit of a guess, but we'll see how we go. So for this beautiful graph where r is 1, r squared is obviously going to be, well, 1 times 1 is 1, or 100%. So if your graph is perfectly linear, then you will get 100% of this value's change can be explained by this value's change. So this might be the exact association between the weight of the cheese you buy and the cost that you will pay, because obviously there's nothing else that explains how much you're paying for your cheese except the weight of cheese you buy, assuming you're purchasing it by gram or kilogram. If there is no linear association, r is 0, then r squared will be 0, or 0%, which will say that none of the variation in this can be explained by variation in that, because there's no pattern. We can't do any predicting. And if r is -1, do remember that r squared, -1 times -1, would be 1, or 100%, because it doesn't have the requirement for negativity. It's just saying 100% of the variation in this variable is explained by the change here. And so we'll write that down. The coefficient of determination, r squared, gives us the degree to which one variable can be predicted from another variable, or the amount if you prefer, rather than degree. Now we'll put in brackets linearly related, because of course to get r we've got to have a linear relationship. Just moving some things there. Now, this will make more sense if we do a few examples. We do need to be able to calculate the coefficient of determination. So the question might say, calculate r squared and express it as a percentage. If r is 0.8, we worked that out before. r squared is 0.64 or 64%. If r is a negative 0.75 and square it. Now, see what happened here. I typed it in, I hit squared, and I got a negative. And you know you shouldn't get a negative because your calculator is programmed to follow order of operations. And order of operations says you do the power first. So it's doing it right. If you want to square a negative on your calculator, you must put brackets around the negative. Brackets, negative 0.75, close your bracket, and then square it. And we will get a positive. And we'll give that, oops, sorry about that, as a percentage. Sorry, I've got an extra light here in the form of my phone to try to make sure I don't have this shadow. It's not working as well as I'd like, but we're doing our best. We also need to be able to calculate r from the coefficient of determination, that is, r squared. So when we're given r squared, please find r. Now we tend to need a scatter plot in front of us to do this, and I'll show you why. So for the relationship shown on this scatter plot, given that r squared is 0.5210, if it was a percentage, you'd just divide by 100 to get back to a decimal, find r. So we'll write an equation. R squared is 0.5210. We want to find r, which obviously means we need the square root of 0.5210. Now, the problem there, as you saw, when I square a negative, I get a positive. When I square a positive, I get a positive. And without the scatter plot, we wouldn't know if r was going to be positive or negative when we did the square root. Because either positive or negative, let's do the square root and get our answer. Square root of 0.5210. Okay, so r was going to be 0.7218, but we don't know if it was going to be positive or negative. That's where the scatter plot comes in. This is a negative relationship, so we know we choose the negative one. R equals negative 0.72. We'll just go to that. So it's a fairly strong negative linear relationship. So if we've got r squared and the direction from the scatter plot, we can find r. But don't forget to check if you need the positive or the negative. So continuing on to do something useful with the coefficient of determination. Now, please do just note, that we'll have to have a quick look at some notation here. So when I say r and in subscripts mathematical, comma, verbal is a positive 0.275, they are using a notation where this is your response variable, the first one, and this is your explanatory variable, the second one. So from their notation, you can tell which one's response and which one's explanatory. And I'll double triple check. Yes, I got that correct. You'll need to know this because obviously the explanatory variable is the one that explains the response variable. And the whole point of r squared is how much the explanatory variable does explain the response variable. Now, when we're interpreting r squared, we're going to use this sentence. The percentage that is r squared tells us what percentage of the variation in the response variable can be explained by variation in the explanatory variable. And then we'd say whether the explanatory variable is or isn't a good predictor of the response variable. So we'll do this one, and we'll pop our answers into that sentence. So carbon monoxide, CO levels in the air, and traffic volume are linearly related, with R value for those two being positive 0.985, so quite a strong positive linear relationship, which you'd expect. This notation means that our explanatory variable is traffic volume. Traffic volume explains carbon monoxide levels. That makes sense. Determine the value of the coefficient of determination, write it as a percentage, and interpret it. So if R is 0.985, R squared, we'll square it, (97%). 0.97 equals 97%. That says 97% of the carbon monoxide levels can be explained by traffic volume. There's not a lot else that's contributing to carbon monoxide levels changing. It's mostly traffic volume, according to this piece of information. It still doesn't actually say it's causative. It's still only a correlation, but the stronger the correlation is, the more confident we can be in making a prediction. And so we can put that into here. 97% of the variation in our response variable, carbon monoxide levels. You don't need to write this little RV, by the way, when you do this sentence, can be explained by variation in our explanatory variable, traffic volume. And because that's a very high percentage explaining carbon monoxide levels, we can say that our explanatory variable, traffic volume, is a good predictor of carbon monoxide levels. We wouldn't put these little brackets of RV and EV. I've just put them there to help you write that sentence. Now that's been quite a long video, 12 minutes. If you would like another example of this interpretation of R squared, I'll do another one. If you think you've got it, don't bother watching the next one. Extra example. Scores on tests of verbal ability and mathematical ability are linearly related, with R mathematical verbal equaling positive 0.275. Now an R of 0.275, that's not a very strong relationship. Remember, this is our EV, this is our RV. Explanatory variable, response variable. Determine, or find, and interpret the coefficient of determination. If R is 0.275, R squared (0.0756). Take a few decimal places, because remember we're going to multiply by 100, and we'll get 7.56%. That is, only 7.56% of the change in some or of someone's mathematical ability scores can be explained by their verbal ability scores. There's not a lot of link between the two. So we write our sentence. 7.56% of the variation in our response variable, which is our mathematical ability scores, we get that from our question, scores on tests of verbal ability and mathematical ability. That percentage of the variation can be explained by variation in verbal ability scores. Oh, sorry about my writing there. So more than 90% of the change in the various different scores in mathematical ability is explained by other stuff than the verbal ability scores. That's not a good link. Just because you've got good verbal ability scores doesn't mean you're going to have good mathematical ability scores. Just because you did badly here doesn't mean you won't do well here. There's not a lot of explanation between the two. And so we'd say that our explanatory variable, verbal ability scores, are not a good indicator. So you'll really need to know the difference between r and r squared and what r squared explains for us.